Section 4.1, Composite Functions. So a composite function, these are the notations for that, and they're all read f of g of x, is the result of inputting the output of one function into another. Or the other way to think about this is you're just inputting one function completely into another function. When considering the domain of composite functions, the thing to remember is that x is in the domain of g, and then g of x is in the domain of f. But what that really means is that the domain of f of g of x is the intersection of the domain of g of x and the new function f of g. And so you have to take two considerations into account, that is, your initial function and the composition, and then look at where those two domains overlap. Now, it is true that we can compose in both directions. So if you have two functions, f and g, you can compose f of g of x. You can also compose g of f of x. But it's not necessarily true that those things are the same. So be careful, the order in which you do these matters. Once again, this notation, f of g of x, g is the inside function and f is the outside function. So now let's just calculate some of these compositions. So here we have f of g of 4 and g of f of 2. Well, there's a handful of ways to do this, but you could rewrite this as f of g of 4. And if you want, you could find g of 4. So g of 4 is going to be 7 minus a half 4 squared. 4 squared is 16. 16 times negative 1/2 is negative 8. And so we get 7 minus 8. 7 minus 8, which is negative 1, which means that f of g of 4 is the exact same thing as f of negative 1, because g of 4 was negative 1. Then, what's f of negative 1? F of negative 1 is going to be 4 times negative 1 quantity squared minus 3. Negative 1 quantity squared is positive 1. Positive 1 times 4 is 4. 4 minus 3. And so f of g of 4 is 1. Let's follow this same pattern. We have g of f of 2. So let's evaluate f of 2. F of 2 is 4 times 2 squared minus 3. 2 squared is 4. 4 times 4 is 16. 16 minus 3 is going to give us 13. And so g of f of 2 is the same thing as g of 13. Then find g of 13, that is 7 minus 1/2 13 squared. 13 squared is 169, so this is 7 minus 169 halves. 7 minus that number. We need to find common denominators, but that's multiplied by 2 over 2. That's our 1 in disguise, so that's 14 halves minus 169 halves, which is 155 halves. Now to calculate f of 1, that is f of 1, we can rewrite it like that. F of 1 here is 4 times 1 squared minus 3. 1 squared is 1. 1 times 4 is 4. 4 minus 3 is 1. And so this is f of 1. But notice that we're calculating f of 1 again. And g of 0, that is g of g taking in 0. G of 0 is 7 minus a half times 0 squared. But that's going to be 7 minus 0, just 7. And so g of 0 is really g of 7. And g of 7 is 7 minus 1/2 7 squared, which is going to be 7 minus 49 halves, which is 14 halves minus 49 halves, which is negative 35 halves. So now we have new functions f and g. We want to find f of g of 4. So let's find g of 4. G of 4 is the cube root of 4. But since 4 is 2 times 2, there's no simplifications that are going to occur, and so it's the cube root of 4. And so that is f of cube root of 4, which is 14 divided by cube root of 4 plus 5. We could rationalize the denominator, so I'm just going to leave this as is. G of f of 2, let's calculate f of 2. F of 2 is going to be 14 divided by 2 plus 5. 14 sevenths, and 14 sevenths reduces to 2. So f of 2 is 2, so that is g of 2. So then that's the cube root of 2, but the cube root of 2 won't simplify, and so we're done. So if we're trying to calculate f of 1, I can calculate f of 1. F of 1 is 14 divided by 1 plus 5, or 14/6, which is 7/3. That is f of 7/3 is the same thing as f of 1. Well, that's going to be 14 divided by 7/3 plus 5. Need to find common denominators, so my common denominator is 3 here. So then I get 14 divided by 7/3 plus 15/3. 7 plus 15 is 22/3. This is then fraction division, which becomes fraction multiplication. So this is 14 times 3 over 22. That is 22 divided by 2 is 11. 14 divided by 2 is 7. 7 times 3 is 21. 21/11ths is my answer. G of 0. So we can start by finding g of 0. G of 0 is the cube root of 0. And the cube root of 0 is just 0, so g of 0 is the same thing as the g of 0, but we've already calculated g of 0 and we found that that is 0, and so we're done. Alright, now it's a little different because we're getting x values and f of x values and g of x values. So we need to figure out what these are based on what's happening in the table. So if I have, first off, f of g of 1, well, let's first find g of 1. Well, come to the table, find x input of 1, and the g output is 0. So g of 1 is 0. Okay, great. That means that then f of g of 1 is the same thing as f of 0. So at this point, we then go back to the table, find the x value that indicates 0. Well, there it is. And then the output for f is -1. And so f of 0 is, so f of g of 1 is -1. G of f of -1. So first off, let's find f of -1. -1 I find here. Then f of -1 is -3. So that's f of -1. So that means this is g of -3. So then we find that g of -3 is going to be 6. And there we are. Do it again. We've got f of -1. So inner function f of -1 is -3. So then this is f of -3. So then find -3. F of -3 is -7. That one's done. Then we have g of -2. So what is g of -2? That is 2. Then I've got this is g of 2. But let's find g of 2. G of 2 is 2. And so 2 is our answer. So now we're going to actually just find the composite functions and their domain. But what's important is remember that when I have a composition of functions, such as f of g of x, the domain of this thing is just going to be the domain of g of x, where it intersects with the domain of the composite function f of g of x. So if it helps, let's talk about the domain of f and g first. Well, the domain of f, that's a polynomial, and so the domain of f is all real numbers. Then if I deal with the domain of g being a constant function 0, constant functions are technically also polynomials, really and truly, and so this domain is also all real numbers. Alright, that looks good for us. So then I need to find the composition f of g of x. Well, what do? Take the function g and plug it into the function f. Well, the function g is just 0. So everywhere we see an x for f, we plug in 0. But notice that that's just going to give us 8 times 0 cubed minus 6 times 0 squared plus 9 times 0. Each one of those terms becomes 0 minus 1. And so now f of g is just the function -1. That's the composition. It's the constant function. But then the domain is, what are the domain restrictions of the final composition? Well, the domain of f of g is -1, there are no restrictions here. So the domain's all real numbers. Well, that mixed with the inner function, where the inner function was g of x, is all real numbers as well. That means that the intersection of those two things is also all real numbers. But now let's find the composition g of f. G of f is just the other way around. Well, take g, and everywhere you see an x, plug in f of x. Well, when I look at the function g, notice I don't see any x's, which means that I have to plug it in where the x's are, and since there are none, the answer is just the function 0. So g of f here is just 0, and the domain is the domain of the inner function f with the domain of the final composition, which is all real numbers, and so the domain here is all real numbers. So let's do another. F of g here, f of g of x, that's just going to be, everywhere we see the x, we replace it with the entire function g, so that's going to be x squared plus 8 quantity squared. So that's f of g of x. Well, first off, we didn't talk about the domain of the inner function g yet. So what's the domain of g? The domain of g, that's a polynomial, so the domain is all real numbers. Then I see my composition is x squared plus 8 quantity squared, but that's just a larger polynomial, so its domain is also all real numbers. And so the intersection of all real numbers with all real numbers is, of course, all real numbers. Then we're flipping it around, g of f. So what happens is we take and we plug in f everywhere there's an x in the g function. So I have this entire function f of x, and I plug it in everywhere there's an x in g, so this is going to be x squared plus 8, or x to the 4th plus 8. So that's then the domain of the inner function f was all real numbers, the domain of the final composition is all real numbers, and the intersection of all real numbers with all real numbers is again all real numbers. Now we want to compose f with f, so take f, plug it back into itself, that is x squared is f, plugged into f is squared, and so that is x to the 4th. But the domain of the inner function f is all real numbers, the domain of the final composition is all real numbers, those intersections are g of g, that is take the function g of x and plug it into the function g of x, x squared plus 8, plugged into g of x is squared plus 8, and to simplify this, that's going to give me x to the 4th plus 8x squared plus 8x squared plus 64 plus 8, that is x to the 4th plus 16x squared plus 72. And the domain of the inner function g was all real numbers. The domain of the final composition here is all real numbers. Their intersection is again all real numbers. So now we actually start getting domain restrictions. So, real quick, what's the domain of f? Well, the domain of f here is 1 minus 7x cannot equal 0. So then minus 1 minus 1, negative 7x cannot equal negative 1, divide by negative 7, divide by negative 7. We get that x cannot be 1/7. So the domain of the function f is everything up to 1/7, excluding union, excluding 1/7, up to infinity. Let's talk about the domain of g. Well, g is 1 over x, and so x cannot be 0. And so the domain of g is from negative infinity up to 0, excluding union, not including 0, up to infinity. So now to find this composite, we have f of g of x. F of x. Take the g function and plug it into the f function. And so that is 5 divided by 1 minus 7 times 1 over x. But now what do we get? Well, we can simplify this a little. This is then 5 divided by 1 minus 7 over x. Be a little careful, this is a compound fraction, and the way to clear a compound fraction as quickly as possible is to multiply by 1 in disguise. That 1 in disguise is going to be the LCD of all fractions, or all denominators that we see. And so the only denominator I see is x, so I'm going to multiply everything by x over x. That's going to give me 5x divided by x minus 7 simplification, and so that is the function f of g. But now notice that this thing gives a new domain restriction, and so at this point we know that x minus 7 cannot equal 0. So that is x cannot equal 7. Alright? And then we also have to deal with the domain of g of x, that's our inner function, and that's where x cannot be 0, right? And so those two values have to both be kicked out because the inner function and the final function domains, any restrictions that we have on those two extend to the restrictions of the entire thing. So that is, our domain is everything but 0 and 7, so from negative infinity up to 0, not including union, not including 0, up to 7, not including union, not including 7, up to infinity, and so that's our domain. Let's do it again, but flip it around. G of f of x. Well, we know the domains of f and we know the domains of g, but let's write it down again. The domain of f is x cannot equal 1/7. Alright, so let's do our composition. G of f. Take f and plug it into g. That's going to be 1 divided by 5 over 1 minus 7x, which fraction division becomes fraction multiplication. That's 1 times 1 minus 7x divided by 5, which is just 1 minus 7x over 5. Notice that our final composition does not have any new restrictions, because if you try to divide by 5, you'll never get 0 in that denominator, which is good. But then you still have to be concerned about the inner function. The inner function domain restrictions must remain, and so the fact that x could not be 1/7 for f, which is the inner function, composed with the domain restrictions of this, which is nothing, give us that our domain is from negative infinity up to 1/7 excluding, union excluding 1/7 up to infinity. Similarly, f of g of x is, take g, plug it into f, that's going to be 1 minus 1 over 1 plus 6x divided by 6 times 1 over 1 plus 6x. We can try to clean it up a little bit. This is then 1 minus 1 over 1 plus 6x divided by 6 over 1 plus 6x. The first good step would just be to turn this fraction division into fraction multiplication. That's going to be 1 minus 1 over 1 plus 6x times the reciprocal, which is going to be 1 plus 6x over 6. Distribute that then is going to give us 1 plus 6x divided by 6 minus 1 plus 6x divided by 1 plus 6x is 1, and so I'm left with 1/6. Then notice that this is 1 plus 6x minus 1, all divided by that common denominator 6, which leaves me with 6x over 6, which is just x. Now, we've got to return to our inner function for its domain restrictions. The domain of g is 1 plus 6x cannot be 0, so that is 6x cannot be negative 1, divide by 6, x cannot be negative 1/6, and so the domain restrictions on our inner function is negative 1/6 gets kicked out. But the domain restrictions on our final composition, there are none. And since there are none, the domain restrictions are only going to be those from the inner function. So that is from negative infinity up to negative 1/6 excluding, union excluding negative 1/6 up to infinity. G of f, so g with f plugged in, so take f, and everywhere we see x on g, plug it in. That's then going to give us 1 over 1 plus 6 times 1 minus x over 6x, which then we get 1 over 1 plus 6 divided by 6 is 1, so that's 1 plus 1 minus x over x. I see a neat little trick here. We could do this as 1 over, I'm going to break up this 1 minus x over the x's. That's 1 plus 1 over x minus x over x, which is then really 1 over 1 plus 1 over x minus 1. 1 minus 1 is 0. That's then 1 over 1 divided by x. But fraction division becomes fraction multiplication, and so 1 times the reciprocal x over 1 is just going to give us x. Once again, we see that our final composition is just x. We'll learn later that this means they're inverses, but for now we just have to deal with the domain. We'll notice that my final composition has no domain restrictions, so then I just have to be concerned about the inner function's domain restrictions. The inner function's domain restrictions are 6x cannot equal 0, and so divide by 6, x cannot equal 0, and so the domain for my composite function is just everything but 0. Negative infinity up to 0, not including, union not including 0 up to infinity. Now we want to decompose a composite function. That is, given a composite function, we want to break it up into possible inner and outer functions. Now, the deal is that we can find f and g. Now, the truth is there could be more than one answer, and there's always the possibility where your inner function is just the identity function x. So let's find some of these, and let's look at some possible options. So if I have h of x, which is really a composition of f and g, being 2x minus 3 to the 5th, let's think about some possibilities. Well, we need our inner function to be g. So remember, this is f of g of x is really equal to the function h of x. And so what are some inner functions we could have? Well, I see that we could make the inner function of course the identity. That's always. And then the outer function f of x could just be the entire function. That is 2x minus 3 raised to the fifth. Or, what else could we have? We could also have the inner function being 2x minus 3, and then the outer function being x to the fifth. Then notice if you compose these, you'll get exactly what we started with. What's another one we could do? We could also say the inner function was 2x, and then the outer function was x minus to the fifth. So here's just some possible choices for what we could get. Let's try it again. I'm going to skip the basic one where we let x be the thing because that's always a possibility. And let's try a couple other ones we could do. Let's deal with the inner function for this one. The inner function could be x squared plus 19, and then the outer function could be the square root of x. Then notice if you compose it, you get the same thing we started with. Or we could have the inner function being just x squared. Then the outer function would have to be the square root of x plus 19. And there may be others, but those are the ones I see right now. So now let's think about this. If we had that a larger composition of functions where f was composed with g was square root of 25 minus 9x squared, which of the following cannot be component functions? Which of these could not work? Well, essentially just put them back together and see if you could get the same thing. So if I've got f of g, plug in g into f. Well, that would give me the square root of 25 minus 9x squared. Well, that one works, so that's not it. That one's fine. B, same thing. This could be the square root of 25 minus 9x squared, but that's what that is, so that one's not it. It's fine. This one, f of x, this one could be the square root of 25 minus 9 times x squared, but notice that's exactly what we had up there, so it's not that one. But then let's try this one. This one is the square root of 25 minus 9x quantity squared, but that would be the square root of 25 minus 81x squared, which means that's not it. And so D is the answer, which is the one that cannot be the component functions. Traders often buy foreign currency in hope of making money when the currency's value changes. For example, on a particular day, 1 US dollar could purchase 0.0856 euros, and 1 euro could purchase 140.0402 yen. Let f of x represent the number of euros you could buy at this rate with x dollars, and let g of x represent the number of yen you could buy at this rate with x euros. So let's write a function that relates dollars to euros. And so that is f of x could be, well, we see that 0.0856 euros could be purchased by 1 US dollar. And so that is, for every US dollar, you get a euro. So we could write this as 0.0856 times x. Then if we want a function that relates euros to yen, 1 euro can purchase 140.0402 yen. So that is the function g of x is equal to 140.0402 times x, where x is euros in this situation. So now let's use those functions to relate dollars to yen. Let's figure out what is g of f of x. And so specifically what's about to happen is we take the function that put in dollars and then gave us euros. We're going to take that function f, plug it into the function that took in euros and gave out yen. So g of f of x. So that's going to be 140.0402 times the function f, which is 0.0856x. Well, then we get a new function, which is the composite function g of f, that is 11 point, and I'm just going to round to 4 decimal places, 9874 times x, where specifically x is the input in dollars and the output is in yen. So then if we want to answer the question, what is g of f of 1,000? That is, if you spent $1,000 on euros and then converted it to yen at this rate, how many yen would you get? And so g of f of 1,000 is equal to 11.9874 times 1,000, which is then going to give us 11,987.4 yen. And once again, I did round to 4 decimal places, just a decision that I made.